Hi class, welcome back. We are on to chapter 9 this week. I hope you had a good week. Last week looking at t-tests, we are going to be focused on the one-way ANOVA, and you're going to learn more about why it's called the one-way ANOVA. And we learned about research designs last week that connected to two different t-tests. We are just going to be focused on the one-way ANOVA for between subjects design. So some quick things that are going to help you connecting. This is called analysis of variance. ANOVA is analysis of variance. So I hope you still remember what variance is. If not, go back and review. A variance is sum of squares over degrees of freedom. So sum of squares and degrees of freedom, also good to know. Hypothesis testing, also good to know. I connected with the independent measures t-test that we learned last week just because it's the same research design. So analysis of variance, or ANOVA for short, is when you are focused on, you're still going to have an IV and a DV. Your DV needs to be data, and your IV is going to be nominal, and you're going to have two or more groupings. Those groupings we can call treatments, we can call conditions, we can call levels. And so all of those mean that same thing. We are still using inferential statistics, so it's going to be a sample data that you're collecting and making inferences to a population. The ANOVA is used over the t-test because t-test is T for 2, remember? So this you're able to use 2 groups, 3 groups, 4 groups, as many groups as you want. And again, when I say groups, it's those different conditions, those different treatments, those different levels of your independent variable. Some assumptions, again, you still need a normal distribution. We're going to have nominal data. We're going to have those groupings or categories. ANOVA is all about, do I see differences in my outcome when I compare against different groups? It is a between subjects design. When we work with a between subjects design, just like T, you have to worry about does each group have too much variance going on, or one group has a lot and one group has a little, so then they're two different. The test that you would run in a stats program is the Levine's test, but basically this is an issue if you've got one group has within that one condition has a standard deviation of 2, another group has a standard deviation of 10, that's too much difference between those two groups, and that's going to cause havoc and your ANOVA will be crap. So that's something that in the real world to consider. We still are doing hypothesis testing. And so with hypothesis testing, you're still going to have a null hypothesis. We're going to still have a research hypothesis, but we're going to see our distribution for our ANOVA statistic is going to be different. I'm going to talk to you a little bit more about some terminology. So again, factor is another fancy name for independent variable. Next week, we're going to talk about the factorial ANOVA, and all that means is you have more than one factor. And so this one-way ANOVA is called the one-way ANOVA because you have one IV. You have one factor. Levels is the name, another name for your treatment groups, your conditions, your groups. Again, that's what are your different comparisons you're making. So I'm going to have one video connected to the homework that's based on an NPR study that was shared looking at 3 different groups, listening to music, listening to books, and then a control group. So those would be my 3 levels or my 3 treatments or my 3 conditions. The basics of ANOVA is you're looking at variance. It's called analysis of variance because we're all about variance. When we look at variance, we are going to look at variance within each group. This is going to be the bottom of our ANOVA formula. So variance within is exactly how you've thought of variance before. When we've had S squared is that variance. Remember, the square root of S squared is standard deviation. So again, this is the idea of dispersion or spread that's going on. So I'm going to look at the variance within my control group. I'm going to look at variance within those individuals who listen to music. I'm going to look at variance within those groups who listen to an audiobook. Again, this example is connecting back to your homework. And so a variance within is we can also call it error. It's why are we seeing these individual differences? You're all listening to music, but you're responding to the DV in a different way. So that's variance within. That's the bottom of your ANOVA. The top of your ANOVA is you're comparing your groups. I'm going to look at the variance between those groups, and that's called between group variance. This is a new type of variance that we're learning, and this is the top of our ANOVA. This one is really going to carry the most weight for us to be able to find support for our research hypothesis. Remember, when we find support for our research hypothesis, we're trying to show the null hypothesis is not true. When I say the null hypothesis is true, I'm saying there are no group differences. Okay? When we talk about ANOVA, the analysis of variance, it is F. So our t-test had T, well, ANOVA has F, and it's actually named F because the guy who just calculated it, discovered it, etc., Fisher. So he made it F. When we call F, you'll see F equals, when you've seen that in the literature, that's an ANOVA. It's an F ratio. It's called a ratio, again, because the top of my F for analysis of variance is between groups. The bottom of my F is within groups. So here is just a conceptual definition of analysis of variance. You have variance between divided by your variance within, which we can also call error. When we're looking at F, you're trying to look at your between groups divided by what you would expect if there was no treatment effect. And so an F, for the F ratio, if you had an F ratio of an F of 1, which I'm going to skip ahead and show you this distribution, that's the F distribution. It looks a little bit different than t-test. We don't have two-tailed, one-tailed tests anymore. We just are, you'll see, we're just going to have them a little bit simpler now that we're working with comparing multiple groups. So this F of 1 is saying my between group variance is the same as my within group variance. That is crap. That means I don't have support for my research hypothesis. There's nothing going on between those two groups. Three groups. Whatever's going on between those 2 or 3 groups is completely absorbed by all the variance within. So that's why that denominator is variance expected with no treatment effect. When we talk about variance, again, some of the things, and you learn more about this in research methods, your within group variance we call error. It's kind of random, unsystematic factors. Your between group variance, you would want to see, I'm seeing group differences. Again, with a strong research design and using random assignment, you're seeing that these between group differences is because you randomly assigned people into those different conditions. Again, that's a true experimental design when you're using random assignment, but I will tell you some ANOVAs don't. Some ANOVAs we just have naturally occurring groups. So again, your F ratio, if your null is true, remember H of O is your null, that means your F is going to be around 1. If your research hypothesis, so the research hypothesis is that each of 1 subscript, if your research hypothesis is true, that means that you have differences, you have significance. And again, when we talk about our analysis of variance, we use that denominator, that bottom of our ANOVA, we refer to it as error, but it can also be called within group variance. Okay, so the other thing I want to show you that connects to the homework is this, that's from your book, connect with that. Do some of these. I'm going to have these as an extra credit option in the homework for you to respond to. So you'd say learning check 1 and then tell me your responses for those 2 problems. Okay. Hypothesis testing now. Hypothesis testing, we can say there are no changes, no groups, there's no treatment effect for my null hypothesis. For my research hypothesis, I will not use any math. I will say at least one is different from the other, or I can say not the null, which is that not H of O. That's because the F test is an omnibus test. An omnibus test means that it's kind of all-knowing. You know there's differences, but you don't know which groups are different because we're going to have to do something called a post hoc for that. So it's an omnibus test. Again, We have a more simplified null and research hypothesis. Step 2 is going to be calculating degrees of freedom. I'm going to talk to you more about that when we connect to our homework. You're going to have a ANOVA table that you're going to fill out. When we do degrees of freedom, we're going to have 2 degrees of freedom now, actually 3 degrees of freedom. We're going to have degrees of freedom between, that's between our groups. So if I had 3 groups or levels or conditions, it'd be n of groups minus 1, which we can also call your number of groups k minus 1. So my degrees of freedom between now becomes 2. My within group degrees of freedom can be big N minus k, which means everyone across all 3 groups minus my 3 groups. Or I can do, well, there were 10 people in group 1, 10 minus 1, plus 10 people in group 2, 10 minus 1, plus 10 people in group 3, 10 minus 1. My degrees of freedom total is simply adding those 2 up, or doing my big N, everybody who participated in the study. Remember, with the between groups design, you're only in one of those conditions. So if I had 3 different groups, each group had 10, my degrees of freedom total would be 30 minus 1. You're going to get some practice with this with your ANOVA table, part of the homework. So with your F, it is always positive. You would never get a negative F value, and it is that ratio. We're going to be learning about degrees of freedom between and degrees of freedom within. So again, if I had 3 different groups, k minus 3, I want you to pause for a minute, calculate what would be your degrees of freedom between. If your degrees of freedom within, also called degrees of freedom error, what would that be if I had 3 groups and each group had 5? All right, so pause and see if you can calculate those things. And I'm going to tell you on the next slide what the answer is. So our answer would be degrees of freedom between 3 minus 1 is 2. Degrees of freedom within, I could do 5 minus 1 plus 5 minus 1 plus 5 minus 1, or I could do 15 minus 3. Both of those are going to give me 12. This is going to be part of your homework. We're going to be working through one of these different ANOVA tables. When we talk about our overall formulas, these are the formulas that I'm going to be focused on. I have a whole lecture that talks about the ANOVA table. So find the ANOVA table, listen to the 5 minutes. It's going to break this down more for you, but this is called your ANOVA table. So we just talked about calculating those degrees of freedom, your degrees of freedoms. And so then, again, this guy for this total could have been n minus 1, 15 minus 1, or you can do 2 plus 12 and get that 14. When I'm calculating it, you're going to see my MS is another word for variance. So variance between is going to be my MS between divided by my degrees of freedom. So 45.35 divided by 2 is 21.68. My variance within, which we call MS within, is my sum of squares within divided by my degrees of freedom. So 64 divided by 12, and that gives me 5.3. My F ratio is going to be 21.68 minus 5.33, and that's going to give me the up 4.7. Again, there's some more explanation and practice with that with your homework. As well as that ANOVA video I was talking about. So again, if I was trying to work with my sum of squares, again, that's another part of this formula. This plus this is this. So sum of squares between plus sum of squares within is sum of squares total. So this asks you that. If I had sum of squares total and I knew sum of squares within, what would be my sum of squares between? And so this plus whatever you're solving for equals 80. So 80 minus 30 equals 50. So our answer is 50. Once we get through that F, again, in the real world, you'd just know the exact p-value, and that's what you're going to know for your homework. If we were working this out by hand, you would have looked in the back of the book for that. You know you have a significant F. This is a significant F. Then I would want to know, well, which groups are different? That's when we get to post-hoc testing, which we call post-hoc tests. A lot of them are planned contrast, but we're going to use that term post-hoc test because we have an omnibus test. F just tells us if it's significant or not. So I'm going to quickly review those 3 different types of post-hoc tests. One is Bonferroni. Bonferroni is basically doing a bunch of t-test comparisons and then having a higher alpha value. Tukey HSD, honestly, significant difference test, is the most common. And then the Chaffee test is more exploratory. So these are 3 different post-hoc tests. You'll see and hear more about that when I review the homework. The other thing that we can look at with this is effect size. So effect size is eta squared or r squared. Again, here's the formula. I'm not going to have you do calculations for it, but again, you look at a chart, small, medium, large. If I had an 80 square 0.4, that would mean 14% of my variance is shared. If I had an r square 1, both of these circles would be overlapping, where one circle represents the IB, one circle represents the DB. I show you how to respond to the literature and give you a couple more slides to review on your own. That's it for my